Stonehenge, the most famous prehistoric monument in Britain, is thought to have been built over 3,000 years ago. The smaller stones, some of which weigh over 5 tons, were brought, it's believed, from the Preseli Mountains in Pembrokeshire. But how did megalithic man get them here? The most widely accepted theory was demonstrated in the 1950s, when a group of schoolboys made the task of moving huge blocks of stone look quite simple. They used logs as rollers or bearings, and the stones rolled easily over the ground. The building of Stonehenge may have been one of the first examples of the use of what today are known as rolling element bearings, and these play an important part in engineering. Rolling element bearings, as the name suggests, use a rolling action to transmit mechanical power. The load is concentrated on a small area of contact. Ball bearings make a point contact. Roller or needle bearings make a line contact. The small area of contact produces a high contact pressure, and that's why rolling element bearings are made in hard, high-strength steel with a very smooth finish. As can be seen from the shaded area on the graph, rolling element bearings tend to be used where high loads are running at fairly low speeds. This keeps wear to a minimum. But there are other examples of primitive bearings, again dating from the dawn of history. When the Egyptians began building the pyramids, they were faced with the same problems as the architects of Stonehenge: how to move massive blocks of stone as efficiently as possible. Each of these stones is as high as a man. It's thought that they devised an equally ingenious system to that used by Stonehenge man. This Egyptian mural shows a colossal statue being dragged along on a sledge. The figure at the front can be seen pouring a liquid under the runners to act as a lubricant. This idea is very similar in principle to the plain bearings in use today. Plain or journal bearings are normally used to house or support a revolving shaft. In most cases, a lubricant is essential, and this plays an important part in the operation of the bearing. We can use a model to show how the lubricant works. Normally, the shaft would rest at the bottom of the bush, but to show the way it works more easily, we've turned it upside down, with the bearing weighted down onto the shaft. When the shaft rotates, it draws the oil round with it, forcing the bearing to rise, so cushioning the shaft. The pressure generated causes the oil to rise in the tubes. If we take a closer look at what happens, this time the right way up, you can see the shaft at rest in the bottom of the bearing. As soon as the shaft starts to rotate, the oil next to it is pulled along with it. However, there's no gap for the oil to go through, so a pressure wedge is formed. It's this pressure that eventually forces the shaft to rise and float on a cushion of oil. We call this hydrodynamic lubrication. We can't ignore the friction set up when two surfaces rub together, especially when a shaft is starting and stopping frequently. If a bearing is to work as efficiently as possible, you have to be very careful as to what material you use. In this standard milling cutter, you can see that the vertical force from the cutting edge is resisted by the yoke which holds the revolving shaft, or arbor. To prevent excessive friction between the arbor and the yoke, it's fitted with a well-lubricated phosphor-bronze bearing. Although brass would be cheaper, there are certain problems associated with it when it's used as a bearing material. For example, if you do use brass, as the shaft stops and starts, you can see that minute quantities of the metal are transferred from the bearing to the shaft.